Hello, everybody. So the talk is named How to Beat Magnus Carlsen in Chess and Become Depressed Along the Way, as one does. So let's get into it. So I am Martin Botka. I am 25 years old and I work for Cyclum currently as an embedded developer, and in my free time I am implementing patches into the Linux kernel. I'm also a guy who takes on a very ambitious project and tries to finish them and fails in mysterious ways. And also a nerd who loves books and cats in general. So, so what we will cover is what are chess engines and how they work, Quanticate as the project and how it started, the evaluations functions and the differences between them as in handcrafted versus neural networks, and then testing of the changes and the impact state on the mental state of the developer. So what you see there is 1 month, or well, part of the month for testing the changes on Quanticate. There is way more, but it couldn't fit into one screenshot. Red are the bad, so they didn't pass or actually lost ELO, and green patches are the ones that actually gained ELO. The center tree actually do not count because they are just progression tests. So out of basically 50, maybe 2 or 3 pass. And to put it into perspective, each of those tests is approximately 50,000 chess games. And it takes, on Ryzen 9 7950X, approximately 2 hours to run around 5,000 games. So it takes a long time to just play a couple of the games, and then also to finish the one entire test is like 1 day. And then imagine having 50 of them in 1 month and getting out of it maybe 3 ELO at the end of the month. So what are chess engines in general? And there is one simple answer to it, just a bunch of code. And well, technically it's the truth, which is the best kind of truth. It's not that simple. So what are they really? Okay, so they are software designed to find the best move to a given chess position. How they do that, we will go through the entire talk, basically. Short history in them and how they started. They were theorized even from Turing, had basically a small theory on how they could be implemented. Until 1997, when there was the Deep Blue and Kasparov battle, or tournament, you could say, they were, well, not that good at chess. And Deep Blue was playing against Kasparov in 1996. This tournament ended with 4 for Kasparov and 2 points for Deep Blue. There was the second rematch, which happened in 1997, and that basically launched the evolution of chess engines as a whole, because that was the first time the chess engine actually beat a human grandmaster at chess. Deep Blue, in basic terms, was really, really simple compared to Quanticate, Stockfish, or any other top-level chess engine. They basically just had handcrafted evaluation, which basically told them how much material each player has, and basic minimax search, which I will explain later in the talk what they are and what they do. And they were running on basically supercomputers of the time. Now, if you open on your phone chess.com or Lichess, you can play against lower versions of Stockfish that are heavily cut down. and are running on limited amount of time. And they will beat you. There is no other way around it. They will absolutely crush you and take your soul in chess, because they can see 50 moves into the future and evaluate them at a scale that we cannot even comprehend. We see chess positions as material and maybe some positional advantage. They see into things that we cannot even imagine, to put it in the basic terms. Now, how they are utilized is the fun way. There are two ways. Either you are a chess player and you are using them to train yourself, or you are using them to analyze your positions and learn from those. Then there is the second, more fun way, and that is you let two chess engines play against them. And what comes out of them is sometimes boring chess, as in they go into a 200-move game where it ends in a draw, which is, well, realistically not that much fun to look at. But then there is the second type of game, which is where they actually one side wins, and you start wondering, like, why does that move work when they play it? For example, like there is a game where some capture seems very, very obvious to a human, like we have a bishop that can take the queen. Queen is worth 9 points, bishop is worth 3 points. And Quanticate just plays a3, pushes a simple pawn that does realistically nothing in the position. And then we start wondering, like, why did it do that, right? And it goes down and down and down and plays the moves, and in the end we discover that, well, if I push that pawn, I can win more material, or I can end the game in a shorter way compared to taking the bishop or the queen, which seems to us humans, well, it's winning, so take the queen, but chess engines want to end the game, basically. Okay, so what is Quanticate? Well, it's one of the strongest chess engines in the world currently. There is the Orion release, which is approximately 23 in the world. The development version of Quanticate is approximately top 13 in the world. There is also other projects, one from Czechia, from here. It is called Motor. That is, I don't remember from top of my head, but it is also extremely strong engine as well. Quanticate is the strongest chess engine in Slovakia currently, and probably in Czechia as well at the time. So how it all started was, well, as any other project starts, you discover that there is something you can do, and that was a YouTube video, basically, that explained like how to make a chess engine and why is it fun. So me and a friend said to each other, let's grab a month and let's see who creates the better chess engine. At the end of the month, Quanticate won the match. To be fair, humiliated, but still won. And then I told myself, well, okay, it's not that strong really, so let's improve it. And then it became one of the strongest engines in the top 100. And then I told myself, well, it's still comparatively low in strength to other engines, so I told myself, well, let's push it a bit harder, so top 50. And then I told myself, well, it's not far away from top 20, so let's get there. And now it's basically just wasting time on writing patches and depressing myself even more. What is it also is free and open source. So if you want, you can right now go onto GitHub, download it, build it yourself, see the code, see what makes it tick, basically. And there are also builds up for Linux or Windows. macOS is currently a bit of a mess to get supported because of their tool chain. But it is possible as well to build it there if you know how. So how do they actually work? And as the comment says, now the actual fun starts. So board representation, because to us we see the board as just a bunch of squares and pieces on them, but if you told any programmer how do you want to represent this, they would immediately think of an array, which is the simple representation, and it's called mailbox in chess engines. Now, it can work and it can be fast. You have to use the right ways to do it. So you have to basically use AVX2, AVX512, and etc. to make them actually fast. That's not really fun for anybody realistically, so we use the less intensive approach, and that is bitboards. So in programming, we have the long, which is a 64-bit number. And if you take a look at the chessboard, it is 8 by 8 squares. So if we do 8 by 8, it is 64. So basically, entire chessboard can fit into the 64-bit number, where each bit represents one square. Now, normal setup is 1-bit board for each piece and 2-bit boards per color. This way, you can have all the bishops in 1-bit board. So each bit is the bishop set on that square. And then you have the color. So basically, black pieces have their own bit board where they are placed, and then you can use AND operation, bitwise AND operation, and get the actual bit of that bishop that you want. So that is the more normal used approach. I, in Quanticade, use the less used approach of 12-bit boards, which is each piece is colored already. So bishop has the white variant and the black variant already built into the bit boards directly, so you can index them per color. And then there is also 3-bit boards for white, black, and then combined together. The both is kind of rarity, because normally you can just bitwise OR the two colors and get the both. But I told myself, well, I can store it so I don't have to compute it at the same time. So it's easier. If it is faster, it's up to basically anybody who can implement it. I haven't tried yet implementing the normal approach. If it's faster, up to see. And as I said, why do we do this if we can just use an array? As I already explained, bit boards are way faster. And now into the actual move generator, where the actual magic happens. Also, right, if I assign numbers to each of those things, then it becomes data, and I can do math on data. And turns out math is really fast. So move generator. Bitboards allow us to use the bitwise operations, and we do that because bitwise operations are really, really fast on the CPU. They are one operation, and you can basically do a bunch of them, not at the same time sometimes, but after each other, and it's still like 2 operations, 3 operations. And each of those operations takes at max like 1 cycle. Why that is important is because chess engines in their own are usually run on the CPU only. They don't utilize the GPU whatsoever. There exists Lila Chess, LC0, which utilizes the GPU, but it does so for the actual neural network. Quanticade and all basically other chess engines of its type utilize also neural network sometimes, but they do so on the CPU. We will get into why they do it and why they don't run it on the GPU, but that will be later. Right, then there is the pseudo-legal instead of fully legal move generator. And the difference between those is basically, imagine you have a position And pseudo-legal position is one where you end up as the position to move in check. We do not check for being in check. Because checking for that is, compared to all of the other things, slow. You have to calculate if every other piece of the opponent is attacking that square. Turns out it's slow, so we do it only when we need to. Now, why don't we check it ahead of time is because in Minimax and Negamax, which we will talk about, we are running through the moves, and if we discover the best move, we return from the position and don't check any other move. So if we can skip ahead, so if we generate all the moves legally, we will be wasting time on checking if the position that we will not even check is legal. We are essentially wasting time on this. So yeah, then magic bitboards on slider pieces. We will not realistically get into them fully because if we did, the entire talk would be about magic bitboards and explaining them. And we don't have time for that. Essentially what they are is a pre-calculated hashboard and bitboard as in own, where you get a hash for that position and you can check from the magic, basically hashing, where the attacking pieces are and where the attacking range ends. If the occupancy board sets a piece at e3 and we have a bishop at e2, or d2, for example, right? And we do not want to calculate on the whole diagonal because the other piece is blocking it. So that's basically what magic bitboards are used to, cut off that range and check if we are generating only for the actual squares we will be actually moving to and allowed to move to. So Minimax, or in more modern ways, Negamax, it is a search algorithm for two-player games. You don't have to use it for chess. It can be used for any other game where there are two players. Negamax is the condensed version of the Minimax algorithm, and it's basically the same result that you get. And now in the more fun part, there is the player one, which gets the maximizing, or what we call it alpha, and wants to maximize the evaluation score, while there is player 2, which is min or beta, and wants to minimize the score, because we will be searching from a position and we will be moving move by move. Now, if we have a position where white is to turn and they have 5 moves, they will not be choosing the move that results in a lesser good position if they have a position already there that's better for them. So they will move there. But then we will move to black pieces and they have another set of moves and they want to minimize the score. So we will know that white player will choose this move, but now we have to figure out what is the minimal score that black will play or choose. And basically from that we have also alpha beta pruning, which will be explained later. And there is the entire tree. So we start from top and move down, or well, actually we have to generate the moves, but we start searching from the bottom to top. Now we start here at 10 and we basically evaluate this position as score of 10, right? So, okay, great. But this node is for the minimizing player and they want the minimal score. So if they have checkmate, aka white position has checkmate, they will not play checkmate. They will choose the position that results in plus 10 or something for them. But basically black will not want itself to be checkmated. And then we move to this position right here, which is maximizing. and we also have to search the other move. So from that position, we have only one move, which results in 5, and then we move back here. Now, maximizing player will want to choose the max number, so that is 10. So we move another way up and basically do the entire thing down the tree and search for every single move in the tree. Some of you may have already figured out the not so optimal situation that we end up with, and that is where alpha-beta pruning comes in. To explain it, we basically start from here, where this is the maximizing player, and they will choose the maximal score. So 3 instead of -1. Now we return to this node where we set alpha at 3, beta is unset, so it is still equal to +infinity. We have to set the bounds of alpha beta to basically the largest numbers on both sides, so -infinity, +infinity. You can set infinity to whatever you want in the chess engine, basically. For Quanticade, it's 31,000, because I use 16-bit numbers to represent them. Okay, now from there, we already know that the maximizing player will get 3. The minimizing player will now have to search also this move. So from this move, we get 5. Okay, but now do we have to search like further? No, because here the maximizing side already has a move better than 3, basically from this. So we will not go there, but we also have to look at the minimizing side. Minimizing side has 3. We already have a move for maximizing side that's basically guaranteed to give them 5 or better. So from here, we already know that the minimizing side will choose 3 instead of 5 or better, and we can prune the rest of the tree here. We don't have to look at it whatsoever. We skip generating tons and tons of moves that we do not need, and we don't have to waste time on evaluating them. This, in turn, basically helps us not waste time, and without changing the actual algorithm in its own. So the result from the algorithm will be the same as without alpha-beta pruning and with it. So that is great for us. Now, one thing is that how do we actually get the numbers at the bottom, right? Like, where do they come from? And we have 2 types we can use. So that is the handcrafted evaluation and efficiently updatable neural networks. Right. So we first will start with handcrafted evaluation. And if we look into it, on the very simplistic side, it's basically a bunch of if-else. If the king is on this position and they can capture a queen, this is good for us because we get positive material. If we can move to this square, but on the next move, we are getting attacked, obviously not so great, so let's not move there. So king safety, material count, then pawn structure. Pawns in chess are evaluated as 1, which may give the person impression that pawns are really not that important, while they are very, very important in chess. And having bad pawn structure can result in you losing the game instead of actually winning the game, because you may not be able to get your pieces out. You may have way more material than the opponent, but what does that matter if I have material more than the opponent if I cannot use that material to checkmate the opponent king? So pawn structure allows us to basically get the pieces out, but also they are very important in endgames, where you do not have any pieces and just have pawns. If you have all the pawns on the same file, that doesn't really help you much if the opponent can just run the h-pawn down the board without you being able to capture it whatsoever with the king. So yeah, that's also part of it. And then there is tons and tons of other little things that you can implement it. That's why it's called handcrafted, because you are the one actually crafting the evaluation of the chess engine. Chess engines did utilize this up until, I think it was Stockfish 12 that implemented neural networks. They can get really, really strong either way. So much that even if you played against a chess engine that has material count only, so basically you grab the white pieces and you discard the black pieces from the material count, you get to a number. So if they have equal material, you will get 0. If they have a bishop more, you will get 300 centipawns. If they have a rook more, you will have 500 and so forth. That is great, but then, well, it is great, but there is the second part, and that is search. If your search is basically searching all of the moves, you will not get far enough in the tree to actually see the advantage of the material. And the point I'm trying to make is essentially, even if you have material count and your search is really strong, Magnus Carlsen cannot beat it. Like, he will get crushed either way. And that is simple material count. The chess engine doesn't even see the positional advantage of this. And it will still regard as a win from the starting position. And I have may mentioned it, I have may not. Chess is a really drawn game. If we start from the starting position, white has a tiny, tiny bit of advantage. We do not know if we are actually allowed to win directly from white perspective, from the starting position, because there are so many possible moves that you can make. After the, I think, 5th move, you have something like 12 million positions that you will end up with. And then imagine that the search engine is calculating to depth 30, which is, well, more than the atoms in the universe, chess positions. Let's say it like that. So we are not searching that. We have to cut some of them, and we will get to that later. But now the more interesting and stronger evaluation is Naninue. Basically what it is a neural network. The UE is at the end of the basically word, but we are saying it efficiently updatable neural network. From the backwards, that is basically a meme in chess engine community because it comes from a Japanese guy who invented, or well, used it first in shogi, which is another two-player game, and they have invented this first to use neural networks. So that comes from them, and we have only basically grabbed it from them, you could say. So neural networks, or at least small ones, are not that really difficult or, well, hard to grasp at first glance, because we have several layers in neural networks. We start from the input layer, then you have the hidden layer, and you have the output layer. At the output layer, we only have one node, which is basically the evaluation score that the neural network will give us. Now, why is there 768 instead of some other number? Is because we have 64 squares in chess board, and we have 12 types of pieces. We have 6 for white and 6 for black. So we have pawn, bishop, knight, rook, queen, and king. That is 6 pieces. We add all of those up. We end up with 12 for both colors. And we combine them, basically. You do just 64 times 12, and you end up at 768. And that allows us to basically give the entire chess position to the neural network and do whatever it wants with it, essentially. It then forwards it to the hidden layer, which is, in this example, 1024 node or neurons. And then there is the funny thing of times 2. Now, in beginnings, we didn't use this times 2. We just used basic architecture. But we have figured out that if you give the neural network both of the sides, so white and black, it can difference between them and learn way more drastically from this. And as it forwards in the network, we then find ourselves at the final output layer, where we just output basically the number that the network thinks. Now, that is one of the most basic neural networks that you can get with. In Quanticade, as you can see, it's a bit more complicated. We start with the 768, which is basically the same, but then we have HM, which means horizontal mirroring. In very basic terms, we grab the position and we check where the king is. If it's between A, B, C, D, or A, B, C, D, E, then you are at one side, and then from E to H, you are at the other side. We split it in half, and now when we are training, we also, and well, evaluating actually, when the king is on this side of the board, so right side, you flip it. This seems absolutely mental at first glance, and even when implementing it, I have found countless bugs to implement it fully. But what it allows the network to do is learn from more positions. Because instead of just training it on, let's say, 1 million positions, this allows you to train it basically on 2 million, because you will always flip the board and feed this information to the network either way, and train it on this as well. So you get more data to teach the network, and from your side as the inference, you just have to flip it sometimes. Now there is also times 13, and that is king buckets. Imagine it as an array where you have buckets. So first row, second row, third, and so forth. You have 8 rows, for example. And if the king is on the first row, you are using this hidden layer for calculating it. And if it's on the second, third, fourth, fifth, so forth, you are using that one instead. This allows us to teach the network the importance of king positions. Why does that matter? Well, if your king is on the starting square and you have not moved it, you are probably in the starting phase of the game, where you have not moved the king anywhere and it's just sitting there and you are moving other pieces. King needs to get very active in the end game, because it is the only piece that actually can move to any squares instead of just pawns. And you also have to protect your pawns with the king, or just run away when you are getting attacked. So if it's on the first row, your evaluation will be way different from when it's on the fifth row, where you are actually way more active with the king, and if the chess position allows it, you are getting better score or worse score or draw, so forth. Now, in Quanticade, I'm using 1536 nodes or neurons. and they are pairwise. So pairwise basically means that we are grabbing half of the neurons and other half, and we are multiplying them together to result in a basically 1536. And why we do it is not so much that it improves the network. It may sometimes improve the network, it may worsen it. Why we do it is because with multi-layered networks, where you have more than one hidden layer, the speed of the evaluation cuts down significantly. So you are not doing 1 second per one evaluation, which is a made-up number. It's usually in the milliseconds, but you are not using that much time, but you are using maybe double the time. Now, you want to cut down on that in a way where you are not actually worsening the network that drastically. And that's where pairwise comes in, and basically you can feed half instead of 1536 to the other layers. Now there is also the times 2, so that's for the perspective, and then we get into the fun part and the hidden layers. They are enclosed in brackets and times 8. We will get there. But basically, from the first hidden layer, we are getting to 60 neurons, from there to 32. Why is there the jump from basically a huge number to small number to bigger number? Is because if we were to use the 1536 and calculate directly to 32, we would be doing a lot of operations. If we can do it the other way around, so instead of 32, we do 16 first, we are cutting down the number of multiplications or basically operations that we are doing in the network inference down to half. So it speeds up the inference drastically, and then we are basically feeding the small number to the bigger number rather fast, and then we are feeding it directly into the output node where we get our evaluation. Now, why is there the bracket and times 8 is because of output buckets. So all of the layers are basically changed based on the material that you have. So if I have a lot of material on the board, I will want to use bucket that is trained on a lot of material. If I have just the king and maybe 2 pawns and the opponent has similar, I want to use the output layers that are trained specifically on this. This helps just basically teach the network about many of the aspects of chess down the road. And now from the actual training, I'm not going to get into it because it is a whole another presentation that we could go in, and science field basically, a new one. But where can you get those positions? There are 2 ways. And in chess engine community, it's kind of controversial because you can get the really good data from Lila chess engine, which basically allows you to generate and train a network that's on a really good level from the start, and you have 13 billion positions to train on. Or you have the slower way, but more fascinating, where you are self-generating those positions. You just simply play games against the same engine or another engine and save those games and save those positions. Then you filter them, do some other things in them, and use that for training. The self-generation method is slower, but basically more fun for the developer, but also a bit more depressing because to match the data that Lila chess generates, it's really hard because Lila chess is not using alpha beta whatsoever. It's using something similar to Monte Carlo tree search, and they are using an actual full-blown neural network that's running on solid GPU. So obviously, we will never match the output from our engine to Lila, where it has an absolutely massive 2 GB network, basically, and we have one that's maybe 16 megabytes. If we do the math and like convert it into size, the first basically network is a couple of kilobytes, maybe 1.2 megabytes. Quanticate star network, and which is all basically other engines use, other than Stockfish. Stockfish is just on a whole another league. We'll see that as well. Quanticate network is approximately 120 megabytes. So now, this is the actual like shown. This is taken from Stockfish, where they have not 768, but 40,960 input layer size. That is because they also have not 64 times 12 as we do, but they do 64 times 64 times 5. Because King is taken in this input matrix, or whatever you want to call it, input layer, as a square instead of a piece directly. It's kind of an advanced version of the King buckets, just for every single square on the board, instead of just having like small section of the board. And then we are just feeding it per layer, or well, per perspective down into 512. Then we are getting to 32 to 32 to 1. Stockfish can allow to do this because, well, they have way more data than we will ever dream of as small engine developers, you could say. They have several hundreds of billions of chess positions that they can train on. We have maybe 20 if you are lucky. So, yeah, we will not get further into it because it's like way more complicated and we would waste a lot of time. So, move ordering. So, if we generate the moves, how do we determine which move we actually look at first? Because it matters a lot. Because in the search, if we can cut off on the first move, we are saving time and improving the histories and directly the move ordering on its own. Essentially, what we say in like chess community is that everything comes down to move ordering. Whatever you do in search may improve the search, but it also improves the move ordering. If your move ordering is really good, where your best move is the first one you try, you are going to cut off instantly, search way less positions than you need to, and just generally like better output from the chess engine itself. So what we actually look at is histories, the piece value, if move gives check, and also something called static exchange evaluation. Now, histories are essentially just an array where you store some number. Now, we have something called butterfly history, which is one of the most basic types you can get. And it basically just grabs the squares that you move from, move to, and the piece that you moved with. Now, once you get a move that is really good, you transform this into the index of the history, where the move would actually be. So you grab the from square, to square, and the piece, and assign it, or well, improve it by some positive number. Now, on all of the other moves, you give it a negative number. So you offset it a little bit, because we want to tell the history that this move is really good. All of the other moves were not good. Why this comes into play is when you can actually use this in the move ordering, and you can basically tell the function, hey, this move has this like number in the history, and if it's really, really big, we search it like first in the like segments that we do. If it's really bad, we want to search it at the last position, like at last in the array, or like basically down of the array. And then comes the piece value, that is for captures and in general. If I want to move the queen has bigger range, and I want to search it first, because we may assume that, well, it may be better. It may not be, but it improves the move ordering a slight bit. Then we have, like, obviously, if a move gives check, we want to search it first because we are attacking the opponent kick. Makes sense. And then we have something called static exchange evaluation, which is if we are given a position and we can capture something, we want to see if we actually lose material or gain material in that exchange. We use static exchange evaluation. What it essentially does is it grabs all of the attacking pieces to that one square and now grabs the lowest piece value, or so the lowest valued piece you can attack and capture on that square, and basically moves forward until you have nothing to capture with. And you see if you end up with a positive score or a negative score. Now this way we can check if we are losing material or gaining material, and on this way we can move moves that actually may capture queen, but down the road they would lose as a rook. We do not want to search those moves first, because even though we are capturing a queen, we would end up in material deficit. So we want to search them down at the list. There is one slight interruption here where move ordering is also something that may make sense and may not make sense. Because, for example, you would assume that if you have a promotion, you would want to search it first. Because, well, I'm promoting a pawn to a queen. Makes sense. I did this in Quanticade, and I implemented the change for approximately 10 elo, when Quanticade was like 3400 elo-wise. So it gained elo. Now we move into a range where we are looking at 3720 elo, and I have just randomly tried to basically remove this from the move ordering yesterday, or actually move day before that, but very recently. And, well, yeah, it's 7 elo to remove it, because that completely makes sense to me. Why not moving the, basically not doing the promotions first is bad. So, yeah, it's also a lot of trial and error. Like, you may think it does make sense, and Chess Engine tells you, well, it loses 30 elo, because why not? So then we also have search, and that is the main part of the Chess Engine, and we will look from iterative deepening, aspiration windows, new move pruning, transposition tables, QSN search, late move reductions, principal variation search, and many, many more, which will not be included, because there is way too much techniques that go into Top Engine that improve it a lot. And not to mention that there are like tons and tons of tweaks that you can do on every single one of these. So let's start with iterative deepening. In the most basic terms, we do something where we are searching in segments. We search first to move 1 or depth 1, and then we search again from depth 1, but to depth 2. Then we start again, depth 1, 2, 3, from the same position. And as the comment says, it may seem counterintuitive, but it improves the strength drastically. And why that is? Because we are using this information from the early positions, or well, early searches that we did for improving the histories. We also use it to improve our range of alpha beta, so we kind of know where we land. This will be used in aspiration windows later, but we kind of know where the position kind of lands in the evaluation range, and then, yeah, it just improves it a lot. Then we have aspiration windows. And instead of searching from basically minus infinity to plus infinity, so for a move that is either a checkmate for the black or checkmate for white, we may say that, okay, well, what if we don't search from those ranges and we actually use the previous information to adjust the score? So we move from we want to see moves only from this range and this range. If we fell outside of those bounds, we extend the range towards the side and search again. So we are doing way more many searches, but in turn, we are basically allowing the engine to improve the alpha beta pruning. Because we will now know that we don't have to look on moves that are really, really bad. So we can just cut them completely. And it's a kind of tuning battle, because if you make the range too big, you are searching way too many moves. If you make it too small, you will do way, way more many searches than you need to. So you need to kind of land in the center where it makes sense to search this much, but also reduce the range that much. Okay, then new move pruning. It kind of makes sense that if we are in a winning position, we want to kind of cut off early because we already know we are winning. One way we can do this is with new move pruning, where we essentially say, okay, our score is so good and we are so winning, let's try giving the opponent literally a free move. We do nothing. Now we get score from that search and we look, okay, is it better than the best we can do? Yes. If doing nothing is still winning, why are we searching when doing something will obviously improve the score itself? So we are cutting off way, way early than we would normally need to, and we are not searching at the full depth. As you can see in the pseudocode, we are reducing the depth by 5. You don't have to reduce it by 5. There are many, many tweaks you can use. For example, you can use the evaluation function and to grab the difference between the worst score you can do and the evaluation, and reduced based on that, also reduced based on depth itself. So if we are in higher depth, we want to reduce further even, and tons of tweaks basically on top of every single one of those things mentioned. But in basic terms, it's really, really easy, like, to understand. Now something that isn't. Transposition table. So if we are searching, we kind of want to save those positions. Because what if we end up at a position where we have seen it like 30 times and we are still evaluating it again and again and again, and searching still that position? We are wasting time. So what we do is every time we see a position that is actually good or has any significance to the search, we save it in the transposition table. And now when we get to a new position and we say, okay, well, this position has the same hash as this position, so it's probably the same position because of hash collisions. There may be like another position that ends up with the same hash. And so we use that information from the transposition table to either cut off directly and not search that move any further, or we adjust the search So we reuse, we extend the search, so forth. Like many tweaks you can do upon this. Like if we have a position that was that ended up in the principal variation search, which is basically the line that gets shown to the user, like this is the best line that we can do. If our transposition search has hit a node where we are from this search, we reuse it, we improve it further, so forth. There is one thing it also does, and as one could figure out, accessing the memory is slow. Like really slow, but also the advantage you get from that is you are cutting down a lot of the positions, and you can tweak the engine a lot with those positions itself, like from the information. As the comment above it said, like even if we don't cut off, we still have a good idea of the position based on the score, which improves search. And it makes it slower, but it improves ELO, and in the end of the day, all we care about is ELO. Quiescent search. So it's a technique that we use for so-called noisy moves. Noisy moves are moves that either capture something or promote a piece, or basically change the board in a drastic way. So captures a capture piece, so we treat them as basically changing a lot. And in in Minimax, you would end up at the so-called leave nodes, basically the last position that we are searching to, and then you would say, okay, well, this is our score that we get from this. And that will be our end, normally. If we implement quiescent search, it basically says, okay, well, we are at the leave node, let's search only the captures in similar way. So we are searching until we are at a position where we have not any captures, we have nothing of that sort. We call that a stable position, and in the end, in the stable position, we evaluate. Now we get basically a position where there are no more captures, nothing that could change the board in a significant way. And so what you end up with at the end is that your search now no longer chooses a position where it may think, okay, well, I'm capturing a bishop. Well, that's great, but you are capturing the bishop with your queen. If on the next move, the opponent chooses to capture the queen, what do? Like from that position, like the score is great because we have captured the queen, but the evaluation function doesn't see that we will capture back. So quiescent search basically gets us to a stable position where we can evaluate that position where nothing will change. Now, late move reduction and principal variation search. It's kind of complicated, but let's try to explain it in a way where it's like really simple. We assume that our move ordering is good, like really good at the time we implement this, and we search the first move at the full depth. So if we said like we are calculating to depth 30, we are searching to depth 30 or improving in some cases. And all the other moves we will search for in reduced manner. So we may reduce it by 4 depths or so forth. So we will not be calculating at depth 30, but at 26, 20, 15, if it's really bad. And we cut down time because we will be assuming that the later moves are bad. So we are not searching them far enough. But if we end up with a move where we are like, oh wait, like this move was ordered really low, but turns out it's really good for us, then we need to search it at the full depth to get the actual correct score for it. Now, how do we determine if that move is good or bad? Is basically a bunch of if-else. Like if we have a move that we have cut previously from the search, we assume that it's bad, so we are reducing the depth. If we grab a move that gives a check, we want to search further to get to a stable position, basically. Many other tweaks on this. And then we have also what's called the PVS, and yeah, basically what I explained already, that we are reducing the depth, but also then searching it again at full depth if we see that it improved. Okay, so there are other things that make the engines actually good, and that is time management. So chess engines don't really understand like how much time I'm supposed to spend on one move. If you gave it the time, it would spend most of its time on that move. And then, surprise, when we get another move from the opponent, we would be like, oh wait, we are running out of time. And it loses on time. Which is really not that great, considering it's trying to win. So what we do in start is basically grab the time, and we divide it by 20. So we assume that there are 20 moves to go in that position, and grab the time. But then in chess engines, we usually play with increment. So per every move that you make, you get some bonus time. We divide this increment by 2. So we grab the half of the increment and add it to our time that we'll be searching. Now, this is the basically most simplest time management that you can do in chess engine where it doesn't lose on time. Top engines change this drastically in a way where we have what's so-called hard bound and soft bound. So we will allocate some time for a move, but we will say, okay, if we are still searching and we have not finished the depth we are searching to, you are allowed to search maximum to this time. If you extend this time or you match it, we will automatically cut off the search so that we do not lose on time. What this allows us to do is basically we allow the search to not get cut off in, for example, depth 20. We would search depth 19 fully, and then we would start searching depth 20, but we already know we cannot finish depth 20. We would get cut and basically get unfinished score and not really useful, so we would be losing time. If we cut off at depth 19, we get extra time that we can use on later moves that may be more important. But soft bounds basically allow us to say that if I'm still searching at depth 20 and I have extended the maximum soft bound that I have, let's search again till we hit, for example, some other time that we have set. This way, we allow to search to finish depth 20 and get more accurate score because we looked further. Then there is what's so generally the speed of the engine is really important. So if we are searching 20 positions per second, it may not perform that well compared to if we are searching 600,000 positions per second. And then that ties to SIMD. So scalar operations on the CPU, AVX2, AVX512, because neural networks improve the speed drastically from this. We will look into that further. And then even if we implemented all of the things that we have described, like NMP, PVS, LMR, RFP, and so forth, they on themselves are not really that complex to understand, but the tweaks that you can do to them change the search drastically. So if we are allowing NMP from depth 1, we would be allowing the search engine to cut off at depth 1, where we are not even finished searching yet, the evaluation, and we would be basically, okay, well, we are cutting off. Yes, we would save time, but realistically, is it good to not even finish that search? No. So we want to do it from some certain depth where we are okay, the search has kind of stabilized and we are not getting complete random noise anymore. And basically, is the developer actually crazy enough to waste all this time to make a good chess engine? And this kind of depends. Are you or not? For myself, it's kind of in the middle already, because at this point I'm making, for example, 100 patches per month, and out of those 100 patches, maybe 2 pass. And then you tell yourself, okay, well, great, 2 patches have passed. Then you figure out that those 2 patches have passed basically with like 2 elo, but that is a sequential probability elo, which is not basically like fixed directly to anything. And it's basically just on the number of games that we have played. And then you do a progression test from your previous version to see like, okay, well, how far have I actually improved from like my previous release? And then you figure out, well, the 2 combined elo that you have gotten equates to approximately 0.5 elo in the real world. And you are like, well, okay, well, that's not really great improvement. You know, Quanticade currently is, Orion was 3696 elo, and I have gotten approximately 82 elo on top of the previous release. Now you may say, well, okay, well, Martin, that makes you like 3770. So basically very, very close to Stockfish. Well, no, because that 82 elo actually gets turned down to maybe 10 at the end of the day. Because compression at the top engines, if you pair Stockfish and Quanticade from starting position, they will nearly always draw. And if you are searching with just one thread on both of them, they will basically all of the time draw, because they are deterministic. Given not time, so given you are searching to a certain depth, time can influence it and change the deterministic, but in general, they will always draw. So we will look into testing the changes and what actually goes to them so that we do not always draw. But then SIMD. So you have 1024 neurons, basically. And then you need to multiply each of them by some number and like transpose it into 32 or 1 or so forth. If you saw any neural network, you know that basically every node is connected with every node, in most cases. There may be skip connections and so forth, but we will not get into that. So you have 1024 numbers that you need to multiply with 32, so it's a lot of operations to do. But what can we do about this? Because if we went for it in like a normal simplistic way, we would be like, okay, let's multiply this number by this number and we get the result. Let's move to another number. That is not really effective because most of our numbers are 32-bit at most, or sometimes 64, but usually we move in the range of 8 to 32. And AVX2, AVX512, Neon, and so forth, like you have many, many architectures that implement basically the same thing with a different register width and different operations, of course. But what this allows us to do is that we can grab, for example, 128-bit register, and we can feed 32-bit numbers into them, stacked, and they would be recognized as, okay, well, this is like in the register, we have 4 numbers. And then what you can do is generate another register of 128 bits, grab another numbers into there, and multiply them or add them or do whatever you want at once. So we cut off, or well, we cut down the time significantly because we don't have to search, like we don't have to calculate every move. Compilers on their own are already smart enough where they do something called auto-vectorization. So they optimize this and they already know that, hey, if this hardware already supports AVX2 and we are basically in a loop where we can do this, let's utilize the hardware. It's all good and dandy until you figure out that handwriting your own SIMD code is way faster, like 20% faster, because the compiler doesn't have a clue about what you are going to do with the number next. So if you know that you are going to do something with the number next and some scalar operation allows you to do that already on that register, you can just do that immediately and not waste time saving it to another number and so forth. And then, of course, like you have different bit with registers, but I think the idea is quite simple. You just reduce time a lot. And now we come down to basically testing of the changes. And this is where the actual fun and depression begins. Because SPRT, or sequential probability ratio testing, I think it's called, is a way of testing changes, but you only get 95% accuracy if it's actually improved or doesn't. Why that is because of the non-deterministic of like time and etc. and the positions themselves. Because you do not want the engine to play against itself from the same position all the time. You would get the same result nearly all the time. If we were to play like quanticate to quanticate from starting position 100,000 times, they would draw maybe like 99,980 games of those in draw. And then you would have maybe 10 losses, 10 draws, or 10 wins. And you would end up at like 0 elo. Even though that change alone that you did may have improved the engine by like 10 elo. You do not see that. So we used books. Books are basically just positions that we have stored. And what we do then is we grab the position and we tell, okay, quanticate will play from like the change that we have done will play from the white side, and then the non-change will play from the black side. They finish the game and it may result in a draw, for example. Now we switch the sides on the same position and we see, okay, the base edition of quanticate has now lost and black has won. So we now see that, okay, the patch has improved us on this specific position. But that doesn't really matter much because it's one position and you want to do this a lot. So we play a couple of 100,000 games like of positions and we switch the sides. And then that's when bounds start to come in, because it's basically telling the probability ratio of what to accept in ELO terms, or yeah, basically ELO terms. 0 is that if it's not gaining any ELO, fail the patch. Like, we do not accept the patch. And if it's gaining 10 ELO, normalized, we accept the patch. Now, in the middle is where the probability comes, because in the middle you have 5 normalized ELO, and you have 50% chance of accepting the change. The lower you get, the lower your chance of accepting that ELO is. So if it is maybe 0.1 ELO, you have very, very rare chance of accepting it, but that's why there is the 95% guarantee that this change will actually improve, because we do not know. So when you are starting out, you usually start with 0 to 10 bounds, but we are already starting to figure out that it's not really good. Let me just sip some water. It's not really good because what happens is so-called small sample size. So you have played maybe 1,000 games and you would tell yourself, well, okay, out of the 1,000 games, we have won 50 times with the new patch and have lost some number of times and have drawn most of them. Okay, great, but does that tell us that the patch is actually any good, or is it just that we have played a limited amount of games where we do not actually know that it's better overall? So in 0-10 bounds, you would have the small sample size tell you that, okay, well, it's plus 13 elo, and you would accept the change. And then you would rerun the test for way more games. So compared to like 3,000 games, you would do 50,000, 60,000, 200,000 games and figure out that your 13 elo patch is maybe 2 elo. So compared to like the difference, there is an 11 elo difference. But the small sample size of those games has told us that it's like 13 elo. So we have to lower the bounds, basically. And by that, we are also reducing the chance of accepting basically small sample size patches that would have passed otherwise. Because for the separator to pass, we have to be outside of the bounds. Like every time you play more games, the elo difference, so you have, for example, 3 plus minus 1 elo. So we have played maybe 200,000 games, and we are now at 3 elo plus minus 1. So that change may be 3 elo, it may be 4 elo, it may be 2 elo. We do not know where in the middle, where in the range it lands, because we have not played enough games yet. So by lowering the bounds, you are basically telling it to play way more games and accept patches that may be gaining lower elo, but you are more certain that like if a patch has gained like 40 elo and it's plus minus 3, then I'm pretty sure that it gains some elo. And it's not small sample size. So we move to 0-5 bounds when the engine is strong enough, or well, now we are moving to it basically from the start. And then we have 0-3 bounds, and that is basically for like top 30 engines around there. Then you can move to 0, 2.5, 0-2. In comparison, Stockfish tests at 0-2 bounds. And then when it comes to long time control, because you don't want the games to take 60 seconds per the game, so we usually test at 8 seconds plus 0.08 seconds increment. So 80 millisecond increment on 8 seconds per move. Now we are kind of slowly moving to 10 seconds and 100 millisecond increment, but patches may scale or scale less with more time given, because we would reach more depth and so forth. So we also, at the top level, want to use, or want to test against like the scaling, actually, if it improves on the longer time control as well. For that, we usually use 40 seconds plus 400 millisecond increment. I use what Stockfish uses, and that is 60 seconds plus 600 milliseconds increment. And this allows us to basically tell if the change is good overall. For example, I have had 2 patches that have passed at 10 seconds with 7 elo, and I was really happy, like finally, some break. And then I have tested it on the longer time control and figured out that, well, it's minus 2 elo. So that is a day ruined. And that's why you are lowering the bounds and etc. But Stockfish uses 0.25 to 1.75 on the longer time control. So it plays more longer games and basically guarantees that it's actually good. And it doesn't go from 0 anymore. And it tells us that I want even tiny improvement, I want to cut off, because we would be searching way too much. So it's basically trying to play less games, because 0.2 would be way too much. And then if you just want to test if patch doesn't lose elo, so it's neutral or like may gain elo, we test with -3 and 1 bounce. This way, we basically accept patch that has lost, I think, 0.4 elo is the maximum that we allow. And we are basically rolling a dice at that point, like, did it actually lose 0.4 elo, or was it neutral and we have just not played enough games yet? So that is the testing of the chess engines. There is also another thing that comes with the books. Most books that we use, or used previously at least, were balanced. What that means is that the position that we have gotten from the book was already basically drawn by the end. That may be good at the beginning of the chess engine, because any change to it would drastically improve it. And from that position, we would already know, like, okay, if I win 20 or 20,000 games from that position and we lose 18,000 and we have like improved by 2,000 games, we already know that it's good, because like the position was drawn. Top chess engines, not so much, because if you give them a slight disadvantage, like -0.3, like Sandy pawns, what you get on the evaluation screen when you are looking on chess.com or so forth, -0.3. And for the lower chess engines, they will either win for black, draw, sometimes win for white, like it's kind of in there, but top chess engines will usually draw that position, either way. So we are kind of forcing them with unbalanced books into playing more drastic openings where one side is already winning, and we are saying, okay, if the patch can draw from like the losing side and can win from the winning side, we are taking it as a win in general. And then we do this many, many, many times. What this allows us to do is get more winning games, get more losing games, and get more draws. But mostly, we are trying to get more decisive games where we either lose or win. This improves the range of the elo, so we are no longer bound to like improvements of 3 elo or so forth, but we may get way more elo at the start of the engine, basically. And the faster the patch will pass with the elo, the easier like you will see if it's good or not. So it's about reducing the number of games, but also in general just easier to tell if this engine is strong or not. Because if it draws that many times from the drawn book and wins that many times and loses that many times, then it's kind of small differences. But by using the unbalanced book, you can extend that like difference a lot. And as the side effect, developer may become addicted to staring at the patches, and their mood will be heavily influenced by it, which is unfortunately true. And now is the time for questions. So does anybody have any questions about anything in that presentation?
I originally wanted to ask you how long have you been working on this, but I already found your GitHub, so I don't.
Thank you. It's on the GitHub, but like I have been working on it since December of 2023. And at the start, it was kind of like in the 2600 range. Over the time, like the first public release, which there is also a release of 0.7, but it's like meh, and also uses stockfish neural network at the beginning. So it's like kind of shamed by the engine dev community because you have not trained your own network. So then I have switched to my own network on Lila data, which is still kind of shame that I'm switching to self-generating, but like that takes time. But then we have improved it a lot, and the first release was 3,300, something like that, which above, it's kind of like saying like above 3,000, you are strong enough to beat any human on world. Like, there is no question if they will win or not. Fun fact about winning against chess engines in general is like, you may assume that, hey, if we grab more humans and let them play against the chess engine, they will win. Like, more humans will usually win against one human, which is true. Then comes the perspective of the engine and shows their absolutely incredible difference compared to us. If you grabbed all humans on Earth and make them Magnus Carlsen, they would still lose against Stockfish or draw. They would never win. Which makes the difference like very striking, because what chess engines see is like completely different to our chess. We cannot even imagine it, because how can you?
What do you mean by curating, making everyone Magnus Carlsen, making them, all of them play the engine?
Like making them like as strong as Magnus Carlsen, which is currently like the...
Yes, but how do you combine multiple people to play one game?
They can think together. Like they can share their ideas. Okay, well, if I do this move, like they will communicate together.
Yeah, I would be very interested how that would look for the entire planet of people, how they
Very, very poorly. It was just a theoretical like showcase that even like so many people would like still not beat it. It's just...
It sounds like what you are saying is that there exists no way to organize those people.
Absolutely. Like even with 10 people, it's already hard enough to communicate that. But it's just to show like the strength difference between us. Any more questions?
I was curious when you were talking about when the engine doesn't play one move, like it's better or now.
No move pruning.
No,
Yeah.
Isn't it against the rules to not play?
Precisely. But we are searching for moves, and basically what no move pruning does in essential is that we assume that, hey, we are winning, and we are forced to play a move, which we'll obviously have to play the move, but we are saying we are so winning at this time in this position that if we do nothing and we give the opponent like literally a free move, so we do nothing and just let them play from the position, which is illegal in the chess rules, yes, but we are just assuming here, right? Like we are not playing a move and we are still winning, right? So when we do a move, we will still be winning and we'll probably improve the score even further. So what we can do is now tell the engine, like, you don't need to search that far away in that position, because that position may occur at depth 25, right? And you would be saying, like, don't waste the time on this position and like on this branch of moves anymore, because we are already winning. And when the time comes and we actually end up on that position, which may be or may not be, we don't know, like how the opponent plays, then when we end up in that position, we search further. Like from that position, like we search it fully, yes, but like when we are searching from earlier position, we cut off, because we are wasting time on position that is already brutally winning for us. I still have like 15 minutes. Are there any more questions?
Yeah, maybe why is it a shame that you are using someone else's framework? I think that you said that most of the improvements are made in tweaking the engine, not in the position evaluation. So
Kind of. everything is basically tied together in the engine. Because if you improve the evaluation, you're improving search drastically either way. If you improve search, you are improving move ordering. So when you improve the network and the evaluation score itself, you are improving search, which by itself improves move ordering, which by itself improves other things. And it basically ties together. So it's kind of this like mess where you do one small change and it may improve the search, but like it may not even end up improving move ordering itself or like etc. It's very cursed on its own. But by improving the network, it can gain a lot of elo. Like by implementing king buckets, when I first implemented, it was around the time I was 3,500 elo rated, and it has gained like 60 elo, which is a lot. And then other changes have basically followed, given that now the search has better like understanding of the position. So no move pruning can now be skipped. For example, if we are not moving, if we are not winning by that much, so we can lower the margin and basically skip pruning those moves or skip them even harder and etc. There is also reverse futility pruning, singular extensions, which are kind of important because what we do in singular extensions is, it was not even mentioned in the presentation, which is kind of sad. We assume that when we have TT move, which is basically a move from the transposition table, that it's good. So what we do next is exclude the move from that search. So we search again from that position, but we do not allow the engine to play this move. And we see if any other move can beat this score, right? If no other move can beat this score, we extend the move by a depth, like 1 or 2, if it's like very, very winning, and so forth. This alone, like singular extensions, can improve the engine by a small margin, like 20 elo at the beginning. If I tried to remove it now from Quanticate, it would be more like 70 to 80 elo. Because the search itself has now been tuned for singular extensions, and the margins have been tuned that we are now assuming that better moves will be evaluated further, and the margins can be lowered, extended, and so forth, and basically all of it ties together. Any further questions? Okay, I think not. So there are the credits. The alpha beta pruning picture was taken from Sebastian Lag, who is a YouTuber. Stockfish team for the Nunue architecture picture, because it's really useful. XKCD, or whatever it's called, for the mad meme on the beginning, and then BGM song for the SIMD picture. And thank you for listening. There is also a couple of people who is, I hope they don't screw up their names. It's World, Stix Doto, Swedish Chef, and Yoshi, who have basically looked at the presentation together and peer reviewed it. All of those people have engines in the top 5. So I hope I didn't make any mistakes while talking about it. If I did, shame me. And with that, thank you for listening.